let's go ahead and jump back to it. So next will come the stack. Hopefully you've talked about the stack before. It is a conceptual area of main memory, RAM, which is designated by the OS when the programs. Wow, that's a mouthful. All right. Anyways, think of the stack as the first piece of memory you want to save and delete your variables to. So you can't do everything in your registers. You want to save it to the stack, and then when you're done with it, you deallocate from the stack. But think about the stack as it grows and shrinks as you push and you pop items. By convention, the stack grows towards the lower memory addresses, avoiding something to the stack. Adding something to the stack means the top of the stack is now at a lower memory address. So it actually grows top down. In other words, it grows down. So if you want to add a piece of data, it's right here. So 0x0 is down here, 0x whatever is up here. And when you add something to the stack, it goes down. That's why when I added, bless you, 8 bytes to it, it shrank the stack because it's growing back up and therefore shrinking the stack. Okay. By convention, the stack grows lower, adding, all right, we talked about that. ESP points to the top of the stack. So, ESP, right there. And let's see, lowest point. The stack keeps track of which functions were called before the current one. It holds local variables frequently used. It is very important you understand the stack very, very well in order to understand program's operation. You hopefully understand the stack from OOP. You did go over an OOP, yes. Cybersecurity people, good, excellent. So it is the stack just like the data structure, where it's handled in assembly. So push. So you can push a word, double word, quad word onto the stack. For our purposes, it will always be a double word, or 4 bytes, because we want to keep our lives simple, and x86 is already way too complicated as it is. You can either push an immediate value or the value of a register. The push instruction automatically decrements the stack pointer by 4. So when you push something, it adds that value here. So we were going to push, give me a number.
20.
2012. Nice. What that does is first, it puts it in here, so that's the first step. So it puts 2012. I'm going to get rid of this arrow because we don't need it anymore. And then it's going to increment, and then the second thing it does is increment the stack pointer to point right here. And so we'll just say, sake of argument, 0x0, 0, and then it would then be at 0x04. Wow, that's hard to see. So let me do it on the other side. And that way, that way I can use bigger numbers. So we'll call it 0x, I don't know, C1004. And then this one will be 0xC1008. So after this push instruction, what is the value of ESP?
XC1008.
8. So the value is 8.
I see.
Right? Or I'm sorry. Yeah, C1008. Right, you're correct.
Okay.
You're correct. I just didn't quite speak right. So it's not the one that ends in 4, it's the one that ends in 8, because that we have pushed something onto the stack. Okay, and again, this is very important, so we get to watch some wonderful slides as we go through this. So we push EAX, so the stack before, where are we right now? Okay, before, where's the push instruction? Oh, push EAX, perfect. You can also push EAX. So if EAX has the value 3, ESP is currently pointing to this address. ESP would then point to, well, yeah, this is the address it points to. It has that value. Afterwards, it will point to this address here, and that value is a 3. Do y'all see what this slide's trying to tell you? it pushed the value 3 onto the stack and incremented the ESP by 4 bytes. So just what I did up here, just in a little different picture. Oh, all right. So if you can push something, you also need to be able to pop something. In this case way, we're going to stick again with double word just to make our lives easier. Put it in a register, pop it in a register, and increment the ESP by 4. So let's go on, we'll do my picture and then the slides picture. So next, we want to pop into, what register you want to pop into? EAX. Thank you, Brian. That was a great idea. I don't know why I capitalized it. What's that?
I'm just a genius.
You are.
No, don't give me that.
EAX equals, we'll say right now, I don't know. So when you're going to pop into it, step 1 is to put that value in. What's the value that ESP is currently pointing to? 2012. So we're going to take that and change it to 2012. That's step 1. Step 2, again, is to take ESP and then decrement it back to here. So, what's the value of ESP? After the pop instruction? 4. It's the one that ends with a 4 because that's where it's currently pointing to. Very important, extremely important. Is the 2012 still there?
Yes.
Yes. The 2012 is there. We have not cleared the 2012. The 2012 is still there. Can anyone, what's that?
Even if it's like pointing to a different spot, as long as it's not cleared, it still exists.
It still exists.
Okay.
Anyone see an issue with that?
It's a memory.
It's not taking up memory. I mean, that value could have just been 0, right?
Push it in, it could be like wrong
Oh, I'm sorry.
number. Like increment.
Let me back up. Security people. Do you see an issue with this?
You're not getting rid of the data.
You're not getting rid of the data. What if you shove the your secret key right here and then you returned without clearing it? And you just so the kernel shoved the key onto the stack, returned it to the user program, but didn't clear the stack. If the user program knew where the kernel shoves the key on the stack in memory that it has access to, it can read it. Obviously, that's a really terrible security flaw, and no one does that. But I need you to start thinking about this in architecture because this problems like what I just described, they're just more complex versions of that is how people break into our systems.
Is
Yes.
this also part of the whole issue, like things getting overwritten? Like you mentioned how your like methods and stuff overwrite information. So with that, if you were to do something else and it
Yeah, so if
pushes to stack,
if a function
overwrite
called
that.
and it messed up your ESP pointer and didn't restore it correctly, oh yeah, totally messes the whole thing up. And that your program, you'll probably get a seg fault. Or it may run and just give you weird errors. Which one's gonna happen? Which one will happen?
I would assume so.
It depends, yes. It depends. Depends on how you messed it up. All right, so that's the pop. So we're going to talk about it here. They're going to pop EAX. So EAX has all Fs. ESP is at 12FF88. So when it pops, I don't like they put undefined here because it still has a value 0x003. It should be considered undefined, but it doesn't actually clear it, which is very important from a security perspective. But notice that the ESP did get decremented afterwards. Everyone good with this? All right. Calling conventions. How code calls a subroutine is compiler dependent and configurable, but there are a few conventions. We're going to deal with the C decal, or the C declaration one, and the standard call. You can go look at these calling conventions here. Basically, what I said is when you call functions, what are the conventions to what registers are saved, what registers can be overwritten, and how do you need to set up the stack before and after you call a function. We're going to stick with this type. I think this is a very accepted way to do it. It's very common, and it is efficient. So C declaration, most common. Function parameters passed onto the stack right to left, basically in inverse order because it's a stack. Saves the old stack frame pointer and sets up a new stack frame. EAX or EDX, so forth, returns the result if necessary. The caller is responsible for cleaning up the stack. Perfect. In other words, the caller who's calling the function sets up the function to use these, and then when the function returns, it cleans up the stack itself. I said that all earlier, so it's nothing, should be nothing new. Let's see, standard call, typically only seen in Microsoft C++. Functions are pushed right to left, saves the old stack, but the callee is responsible for cleaning up any stack parameters it takes. So the way everyone else does it is when you call a function, you set it up and clean up after the function. Microsoft wanted the functions to clean up themselves because, of course, Microsoft decided that the new way of doing things is now the standard way, because that's how Microsoft operates. All right, so the call function is to transfer control to a different function in a way that the control can be returned later when it's closed off. This is important, and does it actually tell you? So, a couple things to keep in mind. Your EIP is where your instruction you're pointing to, and there's going to be a special register that stores where it needs to return once the function is called. Because if you look at the assembly code, you'll notice that in this function, it calls ret. But where is it returning to? It doesn't say in ret where you're returning to. The computer needs to know what instruction pointer you're returning to. Well, what happens is when you do the call function, it's going to automatically save that information for you, and then that way when you call ret, it will return it on your behalf. And then ret returns it, pop the top of the stack into the EIP. Remember, pop increments the stack pointer. The very common way to do this is push where you need to return from on the stack, and then pop it afterwards. That's also interesting from a security perspective, because that means that the next instruction you wish to execute is going to reside on the stack. Does that make sense? The pointer of the next instruction resides on the stack, which means if you're somehow able to change that pointer, you can get a program to jump to a different piece of code and start to execute something else. And if that different piece of code happens to be, print off the security key, could be a bad thing. But we'll get to that later. Okay, we're just going to keep talking about move. So the move is unfortunately going to be your most confusing instruction, even though it should be the simplest one. You move a value from one register to another register, like from EAX to EBX. You can move from memory to register, so at this address, take the value there and shove it into this register. This was called move L for LC64. And you can move from a register to memory, that's called a save word, because you're saving from a register to memory, and that's the move S. You can do immediate to register and immediate to memory as well. And immediate means you just type in the value, but you never can do it from memory to memory. And memory addresses are given in the RM32 format, which I will show you later. Okay. Wow, we got a lot of stuff to go through. It's like death by PowerPoint today.
It's like all my classes.
All your class, are they all death by PowerPoint nowadays?
Yeah.
I can only do death by PowerPoint for so long. All right, let's go do this real quick. We're going to pretend that main is the very first function being executed. I love that phrasing. This is what its stack looks like to start with. So we have main. You may have some local variables. If we want to call, did they change the code in? When main decides to call a subroutine, it becomes the caller because he's the one performing the call. We assume main has some registers that would like to remain the same, so we will save them. We will also assume the callee function takes some input arguments. Okay. I don't like these slides. Good, let's do this. This makes way more sense. All right, so we have main. We push EBP on the stack. We move EBP to the stack pointer so we know where the stack pointer begins. We're going to call sub, which jumps up here, which pushes EBD, saves it off. We're going to move the result beef back in EAX, and then we're going to return. Again, these two instructions here and this one down here are done by convention. In all technicality, they were not necessary for this call to sub, but since we're trying to follow the calling conventions, the C-decal calling conventions, we are going to perform those operations. And so that is returning beef, and then down here we move into foo. So notice when you do call, you're saving off the EIP onto the stack. All right, EIP equals, but no instruction executed yet. All right, let's jump over here, because I think this will make, because we're running low on time, and hopefully this is going to make more sense this time. So this time, this piece of assembly should make way more sense to you than before. If something's confusing, please tell me. So extern printf, extern is just shorthand for external. That means this printf function is external to this assembly file and is defined somewhere else in another file, because you're going to link in printf so you can call printf.
Just more assembly code, right? That has an assembly instruction on how to print it. Okay.
You can, yeah, think of it as assembly, or it's just more binary code. It's really binary code, but yeah, think of it as assembly code that resides somewhere else. Section data, this is where we're going to store data, and we're going to declare something called FMT, aka format, double byte, which is the string EAX equals %x followed by a new line followed by a 0. So this is for printf, because this is what we want to pass to printf, which is this right here, this string right here. Next, section text. So this is going to be our assembly instructions. We're going to declare global main, signifying that anyone who links against this file needs to be able to see this main function. Notice that sub is not global, so no one can link against our sub function. Once we compile this into assembly or bytecode, I'm sorry, not a bytecode, into machine code, that sub label disappears. But by declaring main global, the main label does retain or still stick around. This is kind of like in OOP when you declare something private, because if you don't declare it global, it's now private. But if you declare it global, it's now public because anyone else can link to it. First, we're going to declare a subfunction. We're going to push EBT and save it to the stack. That's to set up the stack. We're going to move our return value beef into EAX, which by our calling conventions is the return value of a function. We're going to store it in EAX. We're going to restore the stack pointer, and then we're going to return from the function. That's what sub does. Again, just for clarity, these two set up the stack. This basically takes down the stack. We didn't need to do this for this function, but we're doing it just for emphasis. Main, again, there's the setup for setting up our stack inside of main, because main is a function. We're going to call sub. Notice we didn't have to set up anything because we're not passing anything to the sub function. So we're just going to straight up call sub. That's actually going to push the instruction pointer of where we need to return to on the stack. Then it's going to call sub, and then once sub calls return, this return, it'll know to jump to the next instruction, which is right here. What does this instruction do? Well, it pushes EAX onto the stack. Remember, EAX was the return value of sub, so we're going to push EAX onto the stack up here. Then we're going to push, well, this is really a pointer to the string, dword format, so we're going to push the memory address of the string pointer, of the string, which is up there, onto the stack. And then we're going to call printf. What is printf going to see? Well, its first argument is what was last pushed, which was the string, and then the next argument is the EAX right here. It's going to do its thing, print it out, and then when it's done, we need to add 8 to ESP. So now I'm going to see if anyone can tell me why we need to add 8 to ESP, even though I just fixed the comment. I pushed twice. So I put two things on the stack, which increased the ESP twice. I need to then decrement ESP, or shrink the stack. And the way you do that, remember, in x86, the stack grows down, not up. So you shrink the stack by adding to it. And since everything, we pushed 2 items, and both items were 4 bytes, 2 times 4 is 8. So in order to restore the stack to the proper location, we need to add 8. Does everyone see that? Okay. Then to exit cleanly, we basically take down the stack frame. We restore EBP to whatever it was before main was called. We put 0 into EAX to signify that we are returning 0 from main, aka successful execution, and then we return. Okay. I don't think I ever actually coded this, or ran this, did I? Well, I created a makefile. NASM F ELF32. So the first thing that it does is calls NASM, saying we're going to create an ELF 32-bit binary. That is just the format that we're going to do a 32-bit binary. ELF is a format that Linux can read. We're going to call it on our func.assembly. And then we're going to use GCC to link in the object code that was created from func.assembly to a final binary. The reason we use GCC is because GCC will automatically link in that printf function for us, so we don't have to go through all the linking ourselves. But since it's a 32-bit binary, we do have to pass M32 to signify we are doing 32-bit compilation, and then we will run it. So we call main, there's the assembly, there's the linking, there's the running, and boom, there's EAX equals beef, which is hopefully not a surprise to anyone. And I can go ahead and call function as well, and it's still EAX equals beef. Okay, great. How was all that? A lot. Because I want to at least get to one assignment today. What's that?
I'd rather you didn't.
Well, we need to at least do something. We're going to add, so a couple other things to do. A to I, that is called ASCII to assembly. It takes a string and converts it to an integer. The point of this function, or the point of this, is we want to be able to call, give me a number. 20. And it prints that out in hex for us. 14 is 20 in hex. I can do 2. There's 2. I can do 200. It's C8 in hex. So it's taking the parameter from the command line, doing something, and then just printing it back out for you. This is so we can actually have input to our program. Another way is that you type it, but I don't want to be doing that. So we're just going to do command lines. So let me go ahead and show you how that looks in assembly. Well, we still have printf. But we also need to declare A to I, which is an external function, part of the standard C library. Notice that we haven't changed FMT, we haven't changed global. Ooh, sub is a little different. Do we even call sub? No, we don't. Let me delete this real quick. Let me make sure that doesn't cause any problems. Sure doesn't. Good. So we don't have sub. Excellent. I love when we have less code. Oh wait, y'all can't see this. Set up the stack frame. We're going to push ECX and then move EAX and ECX onto the stack. Ooh, that's kind of confusing. And then we're going to push ECX and call A to I. All right, what is going on here? Well, we want to get the first parameter from A to I and call and convert it to an integer. Well, how do we do that? Well, we need to pass, where we go, ECX, where we go, EAX, which is the EB pointer, and then ECX, which is the next pointer. So hold on a second. I need to make sure I explain this correctly. The EBP is what is pointing to your command line arguments. And so we need to get the, it's a double pointer, so we need to get the first pointer to argv, into EAX. Then we need to go through argv and get the argv sub 1. Since argv is an array of pointers, each pointer is 4 bytes. Our argv sub 1 is really the base pointer plus 4 bytes, because you got to jump over by 4 bytes to get to argv sub 1. Put that into ECX, push that on the stack, then call A to I in order to do the conversion. And since we popped twice, we need to delete twice. And actually, why are we pushing ECX the first time? Anyone want to take a guess? Because I have no idea.
Because we can.
Let's see if that causes any problems. I didn't think so. Yeah, I don't know why that code was there. We just pushed once. Great. So we get the a pointer to the string. We push that pointer onto the stack, call A to I, pop it. Notice that at this point, EAX has the value from A to I, because by convention, our function returns to the register EAX. So EAX has the integer representation of what we passed in. We're going to push EAX and then format so we can print it, call printf. We push twice, so we need to pop or decrement by 8. And then once printf is done, we need to exit cleanly from this function. Okay, how was that? Very confusing?
Yeah.
Okay, all right.
Honestly, I'm more just weirded out by the fact that semicolons are used for different stuff now.
Yeah, well, I don't know how else to say get used to it than I didn't make this decision. How about that?
Alright, I can take that.
I didn't make this decision to use semicolons. I would have definitely stuck with the C way of doing it. But that was not my decision. You can go blame whoever that guy was from 1977. If he's even alive. What's that?
Thinking like 1977? He might be.
He could be alive. Well, it depends on how old he was at the time.
Oh, true.
Yeah, I mean, if he was 18, sure, he's alive. If he's 50, maybe if he's 50 at the time.
There are a couple hundred-year-old people out there.
I mean, not looking good. Not looking good. All right. Well, that probably seems like a lot, and it was. So we will hopefully return to this on, what's it, Thursday, and hopefully it'll be a little better. Let me go and pause recording.